Good morning, children. This is class 12th physics, unit number 8, atoms and nuclei. This is chapter number 12, atom. Today we are going to start with Bohr's model of hydrogen atom. So Bohr proposed a model for hydrogen atom. And this model, children, it was applicable for some lighter atoms, right, with single electron. With single electron revolving around the nucleus. It is hydrogen-like atom, that is helium plus 2, lithium plus 2, beryllium plus 3 and boron plus 4. Right. So with this Bohr model, Bohr removed the Rutherford's model's difficulties by applying the Planck quantum theory. So he introduced here the quantum theory. Now, children, this is we are aware of this, that this X here represents the symbol for the element, and here, children, A is the mass number, right? The mass is constituted by the nucleus, and inside the nucleus we are having protons and neutrons. So your mass number is the total number of protons and neutrons. So Z is the number of protons plus N is the number of neutrons, right? And children, here capital Z, it denotes the atomic number, that is the total number of protons, right? Okay. Now, children, Bohr, he combined the classical as well as the early quantum concept, and he gave his theory in the form of three postulates, right? His first postulate was that the energy levels, right? The energy levels are quantized energy levels, right? Quantized energy levels. Quantized means they can be counted. They are having a fixed values, right? And in that energy level, the total kinetic and potential energy can have only certain values. As Rutherford said that the orbits can have any energy values. No. Bohr said that they are having only certain energy values in which the electrons can revolve, right? So he allowed energy values corresponding to different orbits of electrons, that electrons they can orbit in the orbits having certain values of energy, and these electrons, when they move in the orbit, when they revolve in the orbit, they do not radiate energy. So these are the stationary orbits, right? These are your stationary orbits. This was the first postulate given by Bohr, right? First is the energy levels, they are going to have certain values only. They are going to have certain values only, having definite total energy, right? That is, they cannot have at random. So these orbits are known as the stationary states of atom or stationary orbits, right? Second is, he said that in the postulate number 2, that an photon is emitted when an electron changes from higher energy orbit to lower energy orbit. So children, when an electron, suppose electron is over here, when it comes down from higher energy level to lower energy level, it is going to lose an photon having energy h nu, right? Next. So children, he said that if we combine them, it is that the orbits, they have a definite energy values, right? They have definite energy values, and they have definite energy values, and the energy is emitted or it is absorbed when photon it transits from one stationary orbit to another. So children, when a photon it jumps from higher energy level to lower energy level, it will emit a photon having energy which is equal to the difference between the energy, right? So the electron will jump from higher energy level to lower energy level, then it will emit a photon of having energy h nu. But children, if it goes from lower energy level to higher energy level, then what will happen? It requires energy, right? So who will give that energy? Photon. So when it goes from lower energy level to higher energy level, it will absorb a photon, right? So absorption of photon takes place when it jumps from lower energy level to higher energy level. Right, children? Now, the third postulate is the children electrons, they revolve around the nucleus only in those orbits whose angular momentum is integral multiple of h by 2 pi. Means its angular momentum is quantized, right? It is having L equals to, this is denoted by L, that is L equals to integral multiple of h upon 2 pi, right? And from class 11th we know that the angular momentum is mvr, that is equals to nh by 2 pi, where n is the integral values having 1, 2, 3 and so on. Let me explain you how it is the integral multiple of h by 2 pi. So this is the explanation for Bohr quantization condition. So children, here what we are having? Here we are having, this is a orbit, right? So this electron can stay in this circular orbit. So the circumference of this orbit is 2 pi r, children, right? But electron, when it is moving, here we are going to consider it to be the wave nature. So what will happen? Along the circumference, we can draw the waves over here, right? So children, if you see, if we count the number of waves, suppose we start from here, this is half wave and this is one complete. This is a one complete wave. So this is the distance from crest to crest. The distance from crest to crest is one wave. That is the wavelength lambda. So here how many waves we are having? This is 1, 2, 3, 4, 5 and this is your sixth wave, right? So here the entire circumference of the circle is divided into 6 lambda, right? So this can have a integral value only. So your circumference of the circle, that is 2 pi r, equals to n lambda, right? And we know, children, that lambda, that is the wavelength, is nothing but it is h by p, where p is the momentum and momentum is mv, right? So this value of lambda, when we put it over here, what we will get? 2 pi r equals to nh by mv, and if we take mvr on one side, you will get nh upon 2 pi. So this is what we said here, that it is the angular momentum is nh by 2 pi. Angular momentum L, that is mvr, angular momentum L, that is mvr, equals to nh by 2 pi. So this is the proof of that. That is angular momentum mvr is equal to nh by 2 pi. Right, children? Now what we are doing? Now we are, suppose here you can see, here we are having this wave. Suppose I open these waves, I stretch them. So this is equals to circumference, that is 2 pi r, right? So here, children, this is the equivalent straightened orbits, right? So this can have, n can have value 3, 4, 5, 6 and so on. So here, this is your Bohr quantization condition. Right, beta? Chalo. Moving next, you are having the Bohr model. So as we know, Bohr said that the electrons revolve around the nucleus in certain stable orbits, right, without the emission of energy. So here, children, the necessary centripetal force is provided by the Coulombian electrostatic force of attraction, because we know nucleus is having charge Ze and electron charge is E, right? Positively charged, negatively charged, they are going to attract. So they are going to attract each other. So the centripetal force is provided by the electrostatic force of attraction between them. Right, children? So let's see its derivation, which is on the next slide. So here it is. Here, children, we are going to derive the radius. We are going to derive the radius of these circular orbits. We are going to derive the radii of the permitted orbits rather. right? So here we know the centripetal force is provided by the electrostatic force of attraction between the nucleus and the electron, right? Now we know, children, the angular momentum is quantized, that is mvr equals to nh by 2 pi. From this, what we are going to do, we are going to make V subject of formula. V is the velocity of the electron, right? So here if we make V subject of formula, then we'll get this equation. This value of V, we will put it in the equation number 1. This value we'll put it over here, right? So we will get this equation. So if we make R subject of 1 R will get cancelled, and if we make R subject of formula, we will get R equals to n square h square upon 4 pi square e square k z m e. Now if you see, children, here there are many constant values, that is h square, 4 pi square, e square, k, m, e. They are constant. So we will keep them together. What are variable? N square upon z. So if we substitute these values, it comes out to be 0.529. So our value is n square by z, 0.529 angstrom, right? So this is your equation for radii of permitted orbits. So here you can see, children, that r is proportional to n square. The radius is proportional to n square. That is, the radii of the orbits, it will increase in the ratio of squares. Means 1 is to 4 is to 9 is to 16 is to 25 from the first orbit, right? So it means your stationary orbits, ये जो orbits हैं, they are not equally spaced. They are not equally spaced, right बेटा? उनके बीच में equal gap नहीं है. The spacing is not equal, right? So children, if we put here, if we put n equals to 1 over here, right? So this is the formula, r equals to n square z into 0.529. So if we consider it for n equals to 1, if we put n equals to 1, we will get this is your ground state. Putting n equals to 2, we get your second orbit, that is first excited state. If we put n equals to 3, we get third orbit, that is your second excited state. Right, children? So this is your radii of the permitted orbits. Now we are going to talk about the velocity of the electron in the stationary orbits. Velocity, now we know, children, that for the formula we have that V equals to nh upon 2 pi mr, right? This we know. Now what we are going to do here, we are just going to put the value of the radius. So if we put the value of radius over here, we will get this equation, right? Here also we are having few constants. If we put all the constants together, we will get the equation of velocity as e square upon 2 epsilon naught ch, cc will get cancelled, right? Zc upon n. So your final equation is V equals to C upon 137 Z by N. Right, children? So if you draw the graph of velocity versus N, so they are inversely proportional, so you get a so you get a rectangular hyperbola, right? And if you draw the graph of velocity versus Z, they are directly proportional, so you get a straight line graph. So this is the velocity of electron in the nth orbit. Right, betas? Again, you are having velocity, right? Over here. If you put n equals to 1, right? This is for hydrogen. Now, if we talk about the orbital time period, so we know time period T is 2 pi r upon V, right? This is simple. Velocity is what? Distance upon time. So velocity distance kitna hai? 2 pi r upon time is capital T. So if you make T subject of formula, you will get this, right, children? So this is, since we know a radius is proportional to n square by r and velocity is proportional to z by n. So if you put this, you will get T is proportional to n cube by z square. So this is your time period of the electron moving in the orbits. Now let's, children, talk about the frequency. Now we know the relation between the linear velocity and the angular velocity. V equals to r omega. So V equals to r omega, we know it is 2 pi f. So F equals to V upon 2 pi R, right children? Now in this, if we put the value of R, we will get this, and here we can see all others are constant, and F is proportional to Z square upon N cube. So this is the formula for frequency, that is, it is mz square e raised to 4 epsilon naught square n cube h cube, right? Now children, let's talk about energy. Let's talk about the energy in the orbits. So energy, we are going to have kinetic energy half mv square. Potential energy is your kZe E upon R. So in half mv square, we will put the value of v square. We will get this equation on putting the value of v square, and then we will substitute the value of r, 2 pi m into r. So we'll put the value of r, and we will get the kinetic energy to be this. Right? Similarly, potential energy will substitute the value of r. We'll get the potential value as this. Right? So this is your kinetic. This is your potential energy. So if you see potential energy is negative, kinetic energy is positive. So if you just assemble all the constants, you will see that potential energy is Ze square upon 8 pi epsilon naught r, and potential energy is negative minus Ze square upon 4 pi epsilon naught r. Total energy is the sum of that. So total energy is minus E Z square upon 8 pi epsilon naught r. So here the negative total energy is negative, which shows that the electron is bounded to the nucleus and it is not free to leave it. Right? So here you can see that potential energy is negative, kinetic energy is positive, and total energy is negative. This we have converted. We have put the value of R, so we're going to get energy is minus 13.6 Z square upon N square electron volt. Right, or by putting the values of all the constants. So this is what we have done. Here children, this is the total energy, and this is a constant whose value comes out to be, this is your Rydberg's constant value is 1.097 into 10 to the power 7 meter inverse. Right, and if you calculate this value, you are going to get it as for the hydrogen, that is 13.6 electron volt. So this is the energy possessed by the hydrogen at the ground state, right, at the ground state. So this is it. So children, here you can see n equals to 1, energy is minus 13.6. Just now we saw electron volt. K shell, L, M, N, O, this you all have done in chemistry, right? By substituting the value of n as 2, 3 in this equation, you can get the value of the energy levels as this, right? Okay, so this is your energy level diagram. As you can see, this is your ground state, first excited state, second excited state, third excited state, fourth excited state. And as you see that when it is going from ground state towards the higher energy state, the gap between them is not uniform. The gap is decreasing, right? So this is the energy level diagram. Now let's talk about some term, ground state. So ground state is the lowest energy state of an atom, right? It is called ground state. So energy, we know it is given by En is minus E1 Z square by N. So for hydrogen, we know it's minus 13.6, right? Energy at the ground state. So that is, if you put Z as 1 and N as 1, you will get it at minus 13.6, right? So this is your ground state. Next, we are going to see that this is for hydrogen ground state, right? This is for L and this is for M. Okay, so these are the energies which we had seen in the previous slides as well. Okay, excitation energy. So an excitation energy is the energy that is given to the electron so that it can get excited. It can jump from lower energy level to higher energy level. तो कितनी energy excited में ली है उसने? That is energy of final state minus initial state. So minimum amount of energy required by an atom to go from lower energy level to higher energy level is called the excitation energy. And if we talk about excitation potential, it is simple. Energy, excitation energy divided by the charge. That is it. That is your excitation potential. Right? Similarly, ionization potential energy. So children, ionization potential energy is the energy required by electron to go from ground to any state. Right? So that is ionization potential energy. So that is the final energy of final minus energy of ground state. And if you talk about potential energy, ionization potential, just divide ionization potential energy by charge. Right? For hydrogen, it comes out to be 13.6 electron volt. For helium plus and lithium plus, they have shown you, it's this. Right? Binding energy, children, energy required to move an electron from any state to infinite is called the binding energy. When for hydrogen, we know it is 13.6 electron volt. Transition of electron. So children, when an electron has to move from higher energy level to lower energy level, तो एनर्जी ज्यादा होती है हायर पे, तो वो एनर्जी उसको निकालनी पड़ेगी. So it will emit it in terms of a photon, and so photon is emitted having energy h nu. That energy is equivalent to जिस स्टेट से आया है, जिधर वो आया है लोअर पे, उन दोनों एनर्जी स्टेट्स के बीच का डिफरेंस, दैट इज E2 minus E1 equals to h nu. That is your transition of electron when it takes place. This much on amount of energy is removed in the form of photons when the electron is jumping from higher energy level to lower energy level. Right? So when the photon is emitted, its energy emitted is the difference between the energies of the two states. Right? Now we know energy is nothing but total energy is minus 13.6 electron volt z square by n. So यहाँ पे n2 जिस स्टेट से आया है, सपोज इट इज n2, जहां से आया है दैट इज n2, और जहां पे आया है दैट इज n1. Right? n2 से n1 jump किया है, so that is n2 by n1. If I take common, if I take 13.6 electron volt and z square common in bracket, I will get this. So this is the formula of energy of the photon emitted when it jumps from higher energy level to lower energy level. Right? And if we have energy, we can find out the photon frequency of the photon. Right? We know the difference between the higher energy and lower energy from where it is jumping to where it is jumping is h nu. So nu is E2 minus E1 by h. Right? So you know the value of E2 minus E1, put it, divide by h, that is your frequency. And wavelength can be found out similarly. Right? V equals to frequency and wavelength. Right? So this is the wavelength, frequency is h nu, wavelength is hc by, so hc by lambda. If you just take lambda, make subject of formula, you will get the wavelength of the photon emitted. Now the spectrum. So the wavelength is given by 1 by lambda is r, that is 1 by n1 square minus 1 by n2 square. Right? Here r is your Rydberg's constant. Children, here r is your Rydberg's constant. Its value is 1.097 10 to the power 7 meter inverse. Right? Now here you can see some series over here. Right? I will explain you with the help of the next slide. So children, the first series, here the Balmer series was given by the Swiss teacher, and here the wavelength equation 1 by lambda equals to r bracket 1 by r2, 1 by r1 square minus 1 by r2 square, r1 square, right, n1 square. So he fixed the lower orbit, to be 2. So here instead of, the equation is 1 by lambda equals to r 1 upon r1 square minus 1 upon n2 square, sorry, n1 square minus n2 square. So lower orbit उसमें fix कर दी, that 2 is your first excited state, n equals to 1 is your ground state, and n equals to 2 is your first excited state. So कहीं से भी अगर इलेक्ट्रॉन जंप करके फर्स्ट एक्साइटेड स्टेट में आ रहा है n equals to 2, then such transaction comes under the Balmer series. So as you can see in this diagram, this yellow part, Here you can see that the electron is jumping from various orbits, but they are finally they are ending up at n equals to 2. So this is your Balmer series. Similarly, various other series were given depending upon the spectrum. That is, if the electron they are jumping at n equals to 3, then it is known as Paschen series. If the electrons they are jumping from any higher energy level to n equals to 4, it's called bracket series. And if the electrons they are coming to n equals to 5 from any other higher energy level, then it comes under P-fund series. And Lyman is when the electron comes to n equals to 1, that is the ground state, from any higher energy level, then it comes under Lyman series. So these are the different series, and these are the wavelengths corresponding to Lyman series, Paschen series, bracket series, and P-fund series. Right? If we find out its values of the wavelength, this is again the formula for wavelength, children, and then it comes out to be the Lyman series falls under ultraviolet radiations. The Lyman series, children, it is falling under ultraviolet radiations. Balmer series is falling in visible. So this is the only series which we can see. For other series, we have to do lots of arrangement. Right? Paschen series, it falls under the infrared region. Right, children? So this is it with this. This chapter is over. Okay, children, we'll meet tomorrow now.